So welcome to day 3 of the workshop, and so third day and final day. So yeah, I didn't receive any question. If you have any, as I say every day, you can pop them in the chat right now, or you can send them to me by email whenever you need. Just side note regarding the assignment. So as I mentioned on the first day, I will post today an assignment that you are all welcome to take, but it's only mandatory for people who are taking the workshop for credits. So I think it's only a few of you. For those who are taking the assignment, whether it's for fun or for credits, I will send you a PDF where everything is explained, and there will have questions for the first part of the assignment, which is a quiz with a link toward the form, a Google form in which you can enter your answer. And then the second part is 2 exercises that I explain in the same document, and for which I will expect you to send me files. I've put the deadline in the document too. So what I propose to do is I have a flexible deadline in 2 weeks. So you can send me whatever you have ready by that time. In theory, it's way more than needed to complete the full assignment. But for instance, if you have some doubts regarding the exercise, or if you have some questions, you can send me the version you have by now at that time, and I will send you a correction. And so you can send me in a month, so 2 weeks later, a final version accounting for the correction if you needed some help to finalize some part. So again, it's all explained in the PDF, and I will send you that today, and also put it in the Google Drive. Also, if I know some of you had to miss some of the sessions because you had conflicts with other meetings or experiments or something like that. So I remind you that all the recordings are available on the Google Drive. The links are in my emails. I will send you a follow-up email today again with the link. You can also find all the functions I talked about and used as examples during the workshop, and also a script called script module 1, 2, or 3, where I put all the different command lines I've used during the workshop, so you can test them yourself if you have any question. I want to double check something. Okay, so with that said, we're gonna jump into day 3. So what we've seen so far on the first day, we saw how the interface is organized, basic command line and syntax, the different kind of variables and operations, and how to write a script. Then in our scripts on day 2, we started to write if statement, for and while loops. We saw more about how to handle matrices and also cell arrays, which are different kind of objects in MATLAB. And we finally saw how to write functions, so how to transform a script into a function that you can easily execute with different arguments. So today we're gonna build up on what we've seen so far and add how to work with files, so notably read external files and write new files. We are gonna see how to plot data, and finally I give a very quick introduction to dynamic system modeling with ordinary differential equations, just to show you a little bit what kind of more advanced things you can do with MATLAB, and also if any of you in the room or you people listening to the workshop afterward are taking more collaboratory workshops, that might be a good first step for some of the workshops that are more on modeling. Okay, so I hope everyone was confident with how to work with functions. If it's not the case, you can ask any question you had in the chat, or again unmute and ask or raise your hand. We are gonna see it again today as we work through some examples. And right now we're gonna see how to add files in our function and link files in our function. So we start just with a straight example, how MATLAB works with files. So there are several things you need to do before actually being able to handle a file. So the first thing you need is to know its URL. So it's either, its path. So it's either something on your computer or it's something here on the internet, for instance. Then you're gonna, if you work on the file that is on the internet, you want to save it on your computer before you start working on it, or in your MATLAB drive if you're using the browser version. So what I do with those command lines, the first two ones are here to just, you see, define. This is just defining two variables that are character string. The first one is a URL. And the second one is the name of the file, the name I want to give to the file. And then I'm gonna save that image that is here. I know it's an image just because I'm telling you. And also because you can see I put a .jpeg at the in the name of the file. Yeah, you will save that document, so here an image, using that function here, URL right. So you have to put two arguments. The first one is the path or URL, and the second one is a name you want to give. So that would have been the same if I directly wrote that here. Then you have to read the import the image in MATLAB, and then you can do whatever you want with it. So here, for instance, I decided to print it. So I show you concretely how it looks like. So I'm gonna go here. As I don't know by heart the URL, I'm gonna look into my notes. Okay, so if I take that, so you can see here, I'm defining the first variable. Second variable. So I have those two ones. Now I can use the function URL right to save whatever object is at this URL with whatever name I put in here. So again, that would be the equivalent of writing, for instance, this. Because this will give the same result. So nothing happens much on my screen, except you might notice that I have here in my current folder, I have a new file. And also, yeah, and that's it. Yeah, so I have a new file here. So it's been written in my, the file has been created in my working directory. Then to have it in my workspace, I need to use the IMRED. So here that's because it's a picture. So the IMRED function, and I need to give it a name so it can be stored as an object in my workspace. Okay, so what mistake did I do? Okay. So yeah, now it's here in my workspace. And finally, I can do whatever I want with it. So for instance, here, that function image will just display it in a plot space. So here it is. So yeah, you should see a pop-up when we have figures in MATLAB, they come on pop-ups. So yeah, don't forget you have to have the file somewhere in your folder. So either it's already here because you're working on your computer, or it's or you have to save it. So you use the function URL write, and you have to give it an URL and a URL and a name. And then you have to import in your workspace. If whatever file you are working with is not visible here in your workspace, then you cannot work with it. And then you can do whatever you after that. Okay, so concretely, if we work with a more useful example, I take again that function we wrote yesterday. That was about printing a gene expression. So for instance, we wrote that yesterday, that function. Okay, we had something like this yesterday. So you can see here, that's one of the things I was telling you MATLAB is helpful with. I have this argument in my function that I actually gonna use later, but right now I just deleted it. It's not called anywhere in the function, so it's a useless argument. And so MATLAB detects that and tells you, it highlights the argument and saying it's not being used, so you can delete it. So that's what I'm gonna do here. Okay, so we had this function yesterday where it was looking for within a, so we created a cell array with three genes with their name and their level of expression. I can find them again here. So I created those ones that I put in my workspace. So I was looking through every one of the gene one by one, and then comparing whether the gene we were looking for, so the gene of interest, was the name of the genes we were currently considering in our for loop. So for instance, if I execute that function, so reminding you to execute a function, you put the name of the function, you have to put the input. So here we have the name of the genes, their level of expression, and here for the gene of interest, I'm gonna put the name of this one. And if I do that, it's returning the level of expression of the gene BCL2. Okay, so that was our function. So now what if we want to work with a bigger data set that has more than 3 genes? So I sent you a link to download a file in the Google Drive. I put it again for those who arrived late. It was also on the, I mentioned it in my email yesterday. And if you go on the, if you're looking at the slides, you can also click here at the same file. So if we open that file, we have something like this. So we have 1, 2, 3, 4, 5. How many columns do you have? 1, 2, 3, 4, 5, 6 columns. And we can see that delimited with tabs, tabulation. And so we have the gene, the function, the reference, accession number, and then we have values at which, like their level of expression, their value for the level of expression. So you can see here the numbers. So it's a bit of a mess when you look for tab delimited files in the notebook. It might be clearer if you look into Excel, but the good thing with opening with a notebook, as it will happen by default with a TXT file, is that you can actually see that it's tab delimited and not like comma delimited or something like that. And that's an information you want when you're importing the file in your in MATLAB. So I'm gonna clear the workspace right now so we can again start from fresh. So to read a file, we have to give 3 information. The first one is what is the name of the file. So here I updated the function so it would run on a file that we import instead of running on data that we type directly, that we generate in MATLAB. So the first information we have to give is the name of the file. So for instance, here that's going to be input file. And so the name here is this one. So you have to, don't forget to take the format, the .txt with it. So we have the input and we have to know the delimiter. So here it's tabulation. So for tabulation, it's that symbol, the \T. If it was a comma, that would be just a comma between quotation mark, and whether they are header lines or not. So here you can see when we open the file, we see that this is not data. That's just the name of the column or the header. So you want to give that information to MATLAB so it knows that you won't treat the first line as data. So I actually put that here so it's clear for you to follow. So here are the 3 information I gave MATLAB: the name of the file, the delimiter, and the header lines. You can see those 3 information are now here. And then we need to import the data, even if they're already on the computer in my case. So now the next step I have to do is to import them in MATLAB, and that's with the function import data. And we need these 3 information that we just recorded. Again, we have to give it a name to that object we're gonna generate with our with the data we're importing. So here I call it A. And if I execute this, you can see now that we have the A object in our workspace. So the important thing to know, if you want to remember just one thing, is that you have to use the import data. If you don't remember exactly which information you have to use, like which argument or input you have to give to that function, you can type help import data, and you will have all the information about the function that are provided. And notably, it's telling you need a delimiter, the header line, and so on. And yeah, and you also have an example here. So that can help you if you don't remember how it works. Okay, now if we click on that object, we see it's a structure with 2 files. So we have we have a matrix of 59 by 1 that are data, and a matrix of 60 by 6, which are cells. So actually what's happening here is the data are everything that are numbers, and you can see it's doubles, and the text data are everything else that are not numbers. So here, text. Okay, we have someone in the chat that's telling me that MATLAB was saying unable to open the file. So I'm not sure exactly what's happening. I think there can be several options. Either there was a typo in the name of the file, or the file is not in your current folder. So first check if the file is in your current folder. If it is, check that you wrote the name right. If you're working on the browser version that is working on the cloud, you actually you should have something at the top saying import data. So if that's what's happening, let me know and we can try to reach the browser version together and see how it works from there. When I said there might be a typo in the text, in the name of the file, maybe one common one is to forget the format of the file. Yeah, let me know if that still doesn't work.
I have a question.
Yeah.
So I already have the file in the folder from the drive.
Okay.
But I also tried to download it using that link, using the URL.
The one here.
Earlier. Yeah, so I tried to use the URL command, but I haven't gotten past that. How would I, if I didn't have the file and I wanted to download it from there?
Yeah, I see what you mean, I think.
Yeah.
So hopefully the person who couldn't really solve it. So for the URL thing, I'm gonna copy paste here, paste it from there. Okay, so I'm gonna store that URL here. So we're gonna have to do the same thing that we did with the image. So first you can either define the variable URL and define the name you want to give to your file, or you can just straight up using that function, URL right. You put the URL here. So I actually never tried on that file, so hopefully that works out. I think it works. I'm gonna call it data.txt. Okay, so that works if you just do that. So you use a function URL right, you put as a first argument the URL on which the data is, and then the name you want to give to your data file, and it will appear here. I can check that it looks fine. Yeah, it does look fine. And then from there, it's the exact same thing. I call it B, but that's going to be the same data set. Here, the input file, instead of being the Mitchell gene data, that's going to be the data.txt. The delimiters and header line are the same, so I am not changing that. I run that, and now I have same B here in my workspace, which has the same structure.
Okay, got it. Thank you.
Great. Okay, if anyone has any other question, hopefully the people who couldn't read it the first time now have solved that issue. Okay, so apparently it's still not working for some people. So the one person is telling me the file is in my computer, but not MATLAB. So can you see it here? So one of the issue might be that you're not working in the right current folder. So you should be able to see the file here. If you don't see it, you either have to change your working directory using the cd command and then put whatever address you want to work in. Or you have to move your file using your, your folder explorer, your file explorer, in that folder here. So for instance, in my case, on Windows, I'm working here in that folder. So if you have to see it here, and then once you're seeing it here, you can try to use the import data function. So the way I use it here, so first you give the name of the file that should match exactly what's here, including the formats, and then give the delimiter and the header line. If it's still not working, maybe you can send me the exact error you get. So for instance, you might get different errors depending on what you type. So for instance, if I put a typo here, I'm gonna have this error. What happens if I put the wrong delimiter? If I put the wrong delimiter, okay, if I put the wrong delimiter, it still works, but you can see it's not read the right way. It's just put everything in one cell, so that's not good. And if I, for instance, don't put any information, I would assume there are default values, so it might still run. Okay, with the default values, it thinks that it still works. So, okay, so it's working now for everyone who had issues in the chat. Okay, so if I understood right, the issue was that it was a working directory issue that wasn't maybe matching between where the file was and where MATLAB was looking for the file. So make sure that your file is in your current folder. So you either have to change your current folder or to move your file to match that. So yeah, anything you don't have here, you won't be able to import here. So for instance, if you're working straight from the internet, from online files, you first have to save them on your computer or your drive on, if you're using MATLAB Online, and then you can try to import it here. Okay, I'm gonna remove B just so we are clean. No, that's not, sorry, that's not remove, that's clear. Okay, okay, so now we have this data file. So now how do we work with that? Because, we're used to work with like matrices or cell arrays or whatever, but not with structure as it's called here. So what we're gonna do is we're gonna define one vector that will contain all the gene expression values we're looking for, and then one vector that is containing the name of the gene. So we will, find again that structure we were using before where we had our cell array that was containing the name of the gene and the level of expression. And so to do that, it's a bit weird with MATLAB, but that's how it works. So you have to use, you see when we look here, we can see there are data and text data. And both those things are like, the first one is a matrix 59 by 1, and the second one is a cell array 60 by 6. So we call our object A, it's here. So you want to call to reach the, we're gonna start with the level of expression because that's a bit more straightforward. To generate a vector that only contain that part of the structure, you can simply use the name of your object dot and data. So that's saying you just take the data part. So you can see here it's called data. Just take the data part of A. So you put A dot data. And if I do that, I have here my vector that appeared. And for instance, if I want to check how it looks like, so I can either click on it and I can see indeed I have values. Or for instance, you can try to print the first 10 elements using that structure we saw yesterday. Actually, it's that way. And you can see you have values that looks like what you were looking for from here. Okay, that's clear for everyone. You can give me thumbs up. Okay.
Sorry, how did you do that view?
I double clicked on here on the workspace. Is that what you're asking for?
Yeah.
Okay. Yeah, when you double click on the workspace, that can be like it's not useful if you're working with values, because that's saying exactly like, you know, just one value saying exactly what you have here. But when you're working with like big vectors or matrices, you can double click here and you see them displayed here. And then you can see here you have variables and editors, so you can switch between the two. Okay, so now moving on to the name of the gene. So that's a bit, it's not that more complicated, but it's a tiny bit more complicated just because the name of the genes are buried with all of the text data. So if we look at our folder, our file again, we have lots of names because we have the name of the gene, or lots of character strings. We have the name of the gene and we have the function of the gene that is also a character string. Then we have the reference, which is the name of the paper it was from, and so on. So here, if we look at the text data, we have more columns. So we need to we only want the first one. And there's another thing is that, so we said the first row was a header. So that allowed MATLAB to, for instance, exclude the first row from the data, so the numbered data, and acknowledge that it was actually only numbers left. But from here, because everything is character strings anyway, it's keeping it. So we have two challenges. We need to first get only the first column instead of the 6th column we have here, and second, get only the value, like all the values without the header. So we want to start here. We don't want to have the gene, otherwise it won't match with the numbers of level of expression we have of so the way to do it, so this time, so before we were calling the data part of the file, so this part. Now we are gonna call the text data. So we use the same structure, a.textData, but this time we say regarding the rows, we want all of them but the first one. So we're gonna use 2 to end, and regarding the columns, we only want the first one, so comma 1. So that's exactly the same structure when we were calling elements within a matrix. Here we're saying on the first dimension, which is across the rows, we want 2 to the end, and on the columns, we only want the first one. And if I execute this, you see it appears here in my workspace. And in both cases, we have 59 elements. So we have an object of dimension 59 times 1. So because we wanted vectors, so they're times 1, and 59, that's the number of genes we have in our data file. And you can see here it's a double because it has kept only the numbers, and that's what we wanted for the level of expression. And here it's a cell because we have the individual gene names in individual cells in a cell array. And you can also check what it looks like. So you can do, as I was doing before, you clicked on it and you can see the names here. Or if you want to do it from the command line, you just type the name of your vector, so X1 genes, and then the subset you want to see for instance, the 10 first elements. And you can see set arrays. It's a set array with that. You can also, if you type it with the curved brackets, then you have the individual strings in each of those positions. Okay, so to summarize what we had to do, first thing is make sure you have the file you are interested in your current folder. So either you already have it on your computer and you just move it where it needs to be, using your folder, your file explorer, the Windows or Mac file explorer, or you don't already have it. In that case, you need to download it from the internet and you use the URL write function. Once you have it here in your current folder, you need to import it in your workspace. And to do that, you need to use the import data function. And once you have it in your workspace, you need to extract the vectors of data you are interested in. And so to do that, you have to look at the structure of your object. So here we have data and text data. You have to know which part you want to call. So for instance, we knew that to get the levels of expression of each gene, we could just take the whole part of the data of the file. And to get the names of the genes, we had to subset only the first column and only the following at starting at element 2. So to call those elements, you have the name of the object. So we call it A before, so that's A dot data or text data. And then you subset using the parentheses, as we were doing before with when we were working with matrices. Okay, let me know if you have any questions. Otherwise, we'll move forward. So here, what I've done in this function is that's exactly the function we had yesterday, but I added the from file. And I added an extra argument now that is the input file. Then I had the delimiter and the header lines. I could have put that in the arguments, but I decided not to because I thought about the scenario where you always have the same structure in your data file. The only thing that change are the values, but not the structure itself. But that's something you could put in your as an argument too, if you think the delimiter will change every time, for instance. Then I put the 3 lines to import the data and extract the vectors I'm interested in. I added a line that is just displaying the data have been loaded, just so you know when you're executing the function that it worked. And then instead of rewriting the function we wrote yesterday, I just call it here. So I'm saying here the output is going to be the output of that function we wrote yesterday that was comparing the level of expression of the gene. So to comparing the name of 2 genes to find the level of expression of a gene of interest. And so it looked like something like that, just to remind you. So you can see like unlock a new trick. You can call existing function in new function. So you can have nested function, like you can have nested loop. So I'm removing this because I think I put for the next step of the workshop. And so you can see here, I run that function exactly like it was written here. So I put the same inputs. And note that we had 3 inputs: the name of the gene, the level of expression, and the gene of interest to which we want to compare the name of the gene. And so when I'm here, this one, the name of the gene is defined here after we imported the data. This one, the level of expression is also defined here after we imported the data, and this one was defined when we call the function. So in short, like those 2 elements, the name and the level of expression, are actually coming from that first argument we put here. Is it clear? Or you let me know if you're confused, because that might be coming fast. All those elements.
I have a question.
Yeah.
So when you had imported your data and you called it A, if there was another row of like numbers, like it was like 2 different replicates of a gene expression, but you only cared about one, you would need to also do like the 2 and comma 1 to like tell it to pick one or the other. So
what you would need to do if you had 2 columns with numbers, so it will again only look at the data part of the structure of the object is only looking at the numbers. So you don't need to do the 2 to end, because the header is always going to be already going to be removed. So you can just put the columns, which is saying take the whole column for the number of rows, and then for the number of columns you would say take only the second one. So you take that.
Okay, I got it. That makes sense.
And so, for instance, if you wanted both of them, you could have something like this, where you say, I want 2 vectors, and the first one as the first replicate and the second one as the second replicate. So again, this is saying you take all the rows, and this is saying you take only the first column. And if you're not sure anymore exactly what's in your rows and columns, you can always you look in your variable, so you double click here, for instance, and you can open, and you see here the name has already been removed, the header has already been removed, so you actually want the whole column, and you have 1 or 2 or 3 column that you want to call. I think, like, generally speaking, that's a good advice to visualize your data as you import them, just to make sure. Sometimes you will have issues, notably when you work with comma delimited files. You can have, if you have a comma in one of the values, and you can actually mess up the organization of the file. And so the first verification you can do is looking that the dimensions are right. So here it's right because we indeed had 6 columns, and we had 59 genes, and plus 1 here for the header. And then you can also click on it on each part to check that, that looks like what you're looking for. You indeed have numbers, you indeed have only 1 column, and so on. Okay. Okay, so as I was saying, work efficiently. If you already have a function that does whatever you want, you can just recall it instead of having to write a new function to do almost exactly the same thing plus an extra step. You can just add your extra step before or after, and then call that that function. Okay, so that was to import data. Now we're gonna see how to export data, or to write a new file. So here is the same. We're gonna have to think about 3 components. The first one is the file identifier. So that's the file in which you want to write. The second one is the command line in which you actually write in the file. And the final line is closing the file. So what MATLAB does is you tell him when you start when you use a file identifier, you're gonna open a file somewhere. So it's more or less like, imagine you're opening a Word document. So you're opening your docx document in Word. So it's opening it. Then when you execute the fprintf function, it's gonna write in it. So we've already seen the fprintf function before to display text, but you can also use it to write text in a document. The only difference is that you have to add an extra argument here. That is the file identifier that's gonna say whatever you want to display, you actually write it in there. And then once you're done, you have to close your file. So you open, you write in, and then you close. So how it looks like. So here I reuse that function we made yesterday, the gene expression. I added a new argument, which is the output file. And you can see here, I opened a file, so with the name output file. We have to add that argument here, W, that stands for writing. So this is important because you can, when you open a file, you can do different things with them. Sometimes you can just read them. You know, when if it's like having the read-only version of a document, for instance, when you download a document that you cannot edit. But here in our case, we want to write in it. So we need to put that argument saying, I want to open it, and I want to open it with the, you know, the privilege, like I can, in a way that I can write in it. If you don't remember how it works, as usual, you can always, either you Google how to write on a file with MATLAB, or either you look for the help of the function fopen, and that will tell you the different arguments you have to put and which are the values that you can put to this for those different arguments. So I opened the file here. The file identifier I chose was FID, feed for short. This is a line that I had before, just saying there is no gene found. In case, as I explained to you yesterday, I like to always have an output generated, if then is the output is saying I didn't find anything, just so I'm sure that my function actually ran. So I was already here before. Then I run my for loop, same that was already here before. I print the level of expression. So this was also already here before, but I added this argument here saying whatever you want to write, you actually write it in that file I just opened here. Then I have an output just so I can keep track on my command window that it actually worked. I finish my loops and then I close my file. So if we do it together, so instead of working on what I already have pre-written, I'm gonna take that one that we had yesterday. Okay, so that was the function we had yesterday. So first thing I have to do is define which file I want to work in. So that's gonna be with the function fopen. I give a name of a file. So I'm gonna call it output file. So it means I need to define that output before. So here, you see here, it's an object. If it was, for instance, I could straight away write this. But the annoying thing if I do that is that every time I run the function, it's gonna create a file with the same name. So they're gonna be overwritten. And I don't want that. So I'm just gonna use a name of an object so I can change the value every time I execute the function. And I have to say I want to write in that file. So I add the value. Then here, instead of print f, and then whatever I want to print, I have to add, I want to print in the file I just opened before. And then when I reach the end, I have to close. So that's function f close and then the name of the file identifier. Okay, so if I save that, so it's a function I already have, I save the function, and if I run it, okay, so here I do have everything. I already have my genes here, and do I have the gene of interest? Okay, I have this and this already defined, so that's fine. I have to define my gene of interest, so I'm gonna do that here. Okay, yeah, I'm gonna use that one so I know it's in there. Okay, so now I define my gene of interest, and I can run my, sorry, I also have to give a name to the file. I have a name for the file, and now I can run the function. So I'm gonna just do that so I won't have any typos. Okay, so that's gonna run the function. We already have those one defined here, those ones defined here. This one is defined just above, and this one is defined here. Yeah. So if I run that, you can see here, I have my export txt that was generated. I also have the output that is print. I can check what that thing looks like. So it's saying gene and the name of the gene and expression and the level of expression. And that's what we ask the function to do. Gene, name of the gene, expression, level of expression. So that's just to show you how it runs. If you work on actual data, I would recommend using, you know, instead of writing gene and expression, for instance, you might want to just print the name of the gene and then the comma, for instance, or the tab. So we stick with the command we had before. And if I print that, if I save that and I run the function again, so I'm gonna close it just to avoid. Okay, so I run again, and now if I check it again, I have something like that. And so for instance, if I open it with, or actually if I open it here, no, it's a text, okay. If I open it with Excel, Excel recognizes it's tab delimited, and you can see you already have 2 columns. So when you save data, try to save them in a format that is easy to read for whatever other, like the other steps of the pipeline are. So, you know, either you're gonna try to read it again in MATLAB, and so here you know that's okay, that's a tab delimited. We're gonna play with it in Excel, and so in that case, comma or tab delimited is also the way to go. Or you might want to send it to something else, like for instance R or Python or whatever, to do some analysis that you already have coded in there. And again, tab delimited or comma delimited are good for that. So avoid writing full sentences and prefer having, you know, data separated by an actual useful separator like a comma or tab. Okay, so now if we move back to our function where we were trying to do it from a file, can I, yeah. Okay, so here I retook. Okay, I have a question in the chat, so I'm gonna address that before I move forward. So someone's telling me that they typed the fprint gene expressions as the name of the function, and they had the error message saying not enough input arguments. So it's probably because either you didn't have, so that's this one. Either you didn't have that defined here, or it was defined here, but you actually didn't give it a name. So check how your function is written in the definition of your function. Do you have that output file argument? because so for the other ones, I'm gonna copy what our colleague had in his MATLAB. What that? Okay, so what's it? So that's what they run, and that's the errors they get. Not enough input argument and error in line 3. The feed output file was probably not found. So I guess this was either not defined in the function. So if it's not defined, you have to add it here, or it was actually defined, but you didn't assign a value to it. So to assign the value to it, you either define the value here before, and then when you run it, you put that, or you can directly, for instance, run it that way. And it's gonna say the fourth argument, which is supposed to be the output file argument, is gonna take that value. Let me know if that.
Yeah, so I did all that. So I did the gene of interest, same as you, CCL5, and that's in my workspace. And then also the output file, it's also in my workspace, the export.txt.
Okay.
So I'm not sure.
So when you look at your function, is the output file an argument that you have to enter?
Yeah, yes.
Okay. So what, are you fine with sharing your screen or?
Yeah, I can share.
Okay. So I think I have to stop and allow you. Okay, you can share now if you want. Okay, so you do have that, and you said the okay, and the error is okay, when you run the fgene expression function, sorry, I should have seen it when you copy pasted. You have to put the arguments that you want to run with. So you type the name of the function again or copy paste it. And then you have to put between parentheses the things that you're supposed to enter. So x1 genes and then x1 results, gene of interest and output.
Okay, got it. Thank
you.
So
it's exactly like, you know, when you're doing math, if you want to get the value y of f of x, you have to write the x to get your y. So I think that should work from there. And so the reason why it was focused on, yeah, okay, so that worked. And I think you have, yeah. So the reason why it was focused on output file and not the other arguments that you also didn't provide is just because that was the first one that was called in the function.
Okay.
So yeah, yeah, no worries. Thanks for sharing. Yeah, when the function runs here, the first arguments or the first input it's gonna looking for is the output file, or the other ones come later. And so yeah, the function will, you know, go step by step, and at the first error it's gonna stop. So that can be misleading because you think there's only something wrong with that one, but it can be, there can be stuff wrong with other variables too if they are called after. Okay, so yeah, okay, so I think we're all good. So I highlighted the 3 things you need to add when you want to generate a file. Don't forget to have it as an argument if you want to be able to change the name every time.
Not sure if you restarted recording. Just
sure. I think I recorded.
No, that's fine. That's fine.
I recorded you.
Totally fine with me.
Okay, thanks. But thanks for the warning. Okay, yeah, so put those 3 elements and put the output in that as an argument in your function if you want to do that in your function. And so here you can see, you can, if I use now the function that write the file, I can do as I was doing before, which is call a file, import a file with all those elements, then run the function, and that's gonna export a file from the whole pipeline put together in one function. Okay, I'm wondering if we should maybe take a break now. You happy with taking a break now? Okay. Okay, so let's take a 10-minute break, and then I'm gonna take you quickly through reminders just so we're sure we remember everything we learned, and then we're gonna see how to plot data, and that's a bit I don't know, more dynamic and funky, so I want you awake for that. Okay, let me stop sharing my screen. And okay, let's meet at 10:55. Okay, see you in 10 minutes. Okay, so I hope you're back. So we're gonna okay. Just to summarize what we've seen so far before we move on to plots. So we've seen how to make if statements yesterday, while loops, and for loops. So just to remind you, for loops and while loops are quite equivalent, although not completely. And if you can, I recommend having for loops instead of while loops. So when I say if you can, is if you know you already know in advance all the steps you want your loop to take. If you don't know that in advance, you can still use while loops, but you have to be careful that you have to declare your variables before the loop and set up the incrementation within the loop. So you don't have index issues that are not recognized or start at the wrong value, and you don't get stuck in infinite loops because your index is not incrementing. We've seen how to generate functions. Don't forget the key errors that we always do at the beginning is not naming the function with the file with the right name. So you have to put a function and only the function, nothing before or after the function, in one dedicated .m file. You have to name that file with the name of your function. So that which appears here. And so then you can execute the function in your command window just by typing the name of that function. And MATLAB will look for the file in which that function is defined. We've seen how to read file and how to write files. Here I put some exercise if you want to practice afterward. You can try, for instance, to transform that script you wrote yesterday into a function or a set of functions that will work on the data that you import and also write a file. So that's exactly what we've done today. Except so far today, except that we were doing it on the gene of interest function, the one that finds a gene that has the right name, the name you're looking for. Here I offer you to do it with the other function we wrote yesterday, or script we wrote yesterday, which was looking for any engine that was expressed above a specific threshold. So I want to make sure we have time to see everything else. So I keep that potentially for the end, and otherwise you can just try to do it on your own, and the solution will be anywhere in the files that I've put on the drive. But we can like briefly see the overview of what we would have to do together. So the first thing is import the file. The second thing is extract the data of interest. So that's part of, more or less part of the file importation pipeline. Then compare each gene to the threshold we want to consider. And if it's above, save it in a new file. So that's gonna look like something like this for the function we were yesterday. So the script we were yesterday. So it becomes a function. So make sure it's defined with the right name and the right arguments. And notably, you have to make sure there is an output file so we can save the output. We open the file, we write in it every time our condition is verified, and then we close it. And then you can put that in another function that will run this, but based on data that you read from a file. And so using the same file, you have to add the input file argument, import the file in your workspace, extract the data of interest by creating vectors that will then feed in your other function, and then run that other function that does the comparison and writing work that we just seen before. Yeah, and don't forget that, you know, if you're training, you have to know how to write a function, but you also have to know how to execute it. So if you do that kind of exercise, don't forget to actually run the function and see whether it works, or if you have error popping up. You can see here the way I did it. So I've used two different strategies during the workshop regarding how to execute function. Sometimes I define the input file, output file, and so on before, and then I just re-put those arguments in the function when I execute it, or I can actually directly write the input file, output file, and threshold here within the command line where I execute the function. So it really depends on, you know, how many parameters you have and what is simpler for you. Sometimes it's good to have things stored in the workspace. So that's what we do when we define all those variables before. Sometimes you prefer to keep your workspace clear and not have too many objects, so you might prefer that option. Okay, so I'm gonna move on to plots, but we can come back to that at the end if we have time. No. So this part is like there is very few coding involved, so I really encourage you to do it in parallel with me, so you can you know, start playing with plots yourself. So it's pretty straightforward. The function to create a plot with MATLAB is plot. So before starting that, I'm gonna clear my workspace and we're gonna do that together. So I won't need that anymore. Okay, I'm gonna empty that, clear the workspace and clear the command window. Okay, we're starting fresh. I'm gonna go back in the right one. Okay. So, okay, if you want to make a plot, you actually have to have data first. So we're gonna create some data. So we're gonna do it easy. We're gonna create a vector that goes from 1 to 100 every 5 units. And we need, you know, if we want to plot, we want X and a Y. So the Y would be, for instance, we're gonna do 2X. Okay, so I create those two variables, they're here. And now I can plot them. And here it is. So again, MATLAB will have windows popping up with figures when you generate figures. So you if you don't see anything happening, sometimes it's, I don't know, because like the window can open in the back. So just check if you have another window open here. Okay, so that's easy. Now you can do tons of things to customize your plot as you want. So a few things we're gonna see together. So you see when we use a plot XY function, we have just a line plot. So sometimes it's not the more appropriate. I don't know if you, for instance, if we do something like x square. Let's do 2x square. Oh yeah. Yeah, do it that way. Okay, so I think that's because I have you can see I'm not using MATLAB every day. Okay, so for instance, when we have something maybe a bit more curvy, we might want to know actually how many points were collected instead of just having a line. So the function for that is scatter. So if I do this, and I look at my window again, I have here I have dots instead of having a line. So I can see exactly which value were observed. So the function for that is scatter. In some cases, you might want to have both on the same. Okay, so I'm gonna do it that way so you can see what's happening. So for instance, if I do, I use the hold on command. So you can see when I did the scatter, what happened is that it erased the line plot and put a scatter instead. Now, if I use the hold on and plot, it's gonna keep whatever I already have and just add whatever you want to add at the top of it. So that's useful if you want to either, like we're doing here, have the same variable represented in two different ways, so with the line and with the dots, or if you want to represent two variables on the same plot. So we've seen plot, we've seen scatter, and we've seen that you can, if you use hold on, you have both on the same window. Okay, so that's more or less the same thing I was already doing. Okay, so you can see what I got a few error messages because I forgot MATLAB was thinking matrix wise even when you're using only a vector, and I actually had to add the dot to make it work element wise. The reason I was confused is because I mostly work with R, which mostly works element wise. Yeah, so don't forget about that. But I guess when you plot, that's a good way to check that it's doing whatever you want to do. Okay, you can add other elements to your plot. So for instance, we can add labels on the axis and titles. And for instance, grids, and we can also choose, so grids are the background grid here. Also choose if you want to constrain the axis to be the same, yeah, to be like on the same scale with axis equal. So let's do that. So if I use figure, what's happening is my figure that I had here, that will open a new figure. So that will still keep the old one, open a new figure, but you see it's empty for now. I'm just gonna close this one because we're not gonna use it for now. And I try to have you see everything. So I still have my X and Y defined. I guess we can, yeah, let's go to the sinus. We can let's do the plot and the scatter together, and then so if I run that, my figure was updated. So you can see it's it's not as pretty. I'll increase the step. So I'm gonna open a new figure just so I don't have the ugly one in the back. And close that one. Okay, so maybe the scatter is a bit too much here. I'm gonna remove the scatter. So I can remove just by commenting from and just have that one. Okay, that's nicer. And now we can add, as I was saying, for instance, X label, that's a function, and you put as argument whatever you want to put. So here is X, and Y label is at sin of X. And we're gonna put a title. So you can see if you execute stuff one by one. Sorry, I'm struggling with the Zoom window that keeps popping up right where I want to go. Okay. So if I execute those one by one, you can see they appear as I execute them. Yeah, the other things we put was the grid on. That's gonna have us get a grid appearing here in the back, and the axis equal. That's gonna constrain the shape. It's very not gonna look very pretty here, but yeah, that's yeah. Yeah, you can change the ratio of the axis as needed. So that's, for instance, useful if you want to plot several, if you have several plots and you want all of them to be on the same scale, you can constrain the scale with that kind of function. As I was saying, you can overlay plots. So for instance, I did it before with the scatter and the line, but you can also do it with for instance, if you have two functions you want to plot, or two variables you want to plot. So here, if we do it with the sinus and the cosinus, because we have the hold on, so I'm gonna open a new figure again. So so we start clear and we're gonna execute that. And you see here we have both, and they have like colors attributed by default. And you can, if you want, you can actually change the colors. So for instance, when you execute the plot function, instead of just giving the argument X and Y, you can add information. So for instance, when I put that, it's saying it's gonna be a dash line that's gonna be blue. And if I put that's gonna be the dash / dotted line, and it's gonna be green. If you want more options, you know, I don't know everything at the top of my head. What I recommend is, you know, just Googling how to put an XZ color on the plot or something like that. But we see another very convenient stuff with MATLAB very soon. So you can see here it followed whatever I asked. You can constrain the limit of the axe. So for instance, here the axis equal wasn't great, but if I want to just zoom on what's happening in the middle, around, yeah, let's say minus 0.5 and 0.5. I can use that, and that's gonna, yeah, I forgot the parentheses. That's gonna zoom on whatever I want to zoom on. So you can see here the mistake I made is I put the parentheses on the wrong side, but MATLAB find it for me. So that's zoomed on whatever I wanted to be zoomed on. And then you can also use subplots. If you, instead of having the two at the top of one another, you can have them side by side. So that's the subplot function. So the way it works is you first open your figure. You define your variables that can be done after, before you open the figure actually. And then you open one subplot, you plot whatever you want to plot in there, add whatever legend you want, and so on. And then you open your second subplot and you put the same information. The way it's coded is so with the function subplot, and then you put a dimension. So I want one row and 2 columns. And for now, I'm focusing on the first element. So sticking with that, I'm gonna open a new figure. And I can do subplot. So my new figure is, I'm gonna close all that. I have, so if you run like me, you always end up with a billion windows with figures. So when I do that, that's telling MATLAB I'm creating 2 subplots and I'm focusing only on the first one. So for now, we have the window appearing, but nothing on it. And then you can put whatever you want on it. So for instance, I'm gonna copy that. If you want, you can also add a legend that's gonna be only for that plot. Or that subplot. Here it is, and then I can do the same thing with the second subplot. And here it is. Okay, that's not the nicest plot, but you get the idea. Okay, and then yeah, if you're struggling like me with having too many windows open, you can just use the close function, and that's gonna close all your figure windows. Okay, so some of the plots you can do are, for instance, bar plots. So if we work again with our data that we imported earlier. So I'm just gonna copy, I don't know if I have it here. I'm just gonna rewrite it, okay. I'm gonna close that. So we're gonna see if I remember well my command. Yeah, I keep telling you that we always Google stuff when we code, but the other thing we always do is just copy pasting from previous code we've written. And so it's really hard to just write something straight away without making any typo. Let me just find the name of the file again. So I put the name of the file, I put the delimiter, so here it's tab, and then I put the number of header lines, which was 1. Okay, it worked. And then I define the values I'm interested in. That's the one, the text data. And so this one was from 2 to end, and then the first, and then the second one is just the data, and that was all of them. Okay, so Frida works too. Okay, it worked. So okay, so now I'm gonna make a bar plot out of those data. So the function here is bar, and I'm gonna focus on the expression level. Okay, and so if I plot that, I have something like that. So that's what we got. Now what we want, instead of having the numbers here, we would like to have the name of the genes, because otherwise it's not, you know, not very interesting. So we can use this thing. So wait, what I did here, I think yeah, I skipped a step. Yeah, what I was offering to do in that function is, so first thing is we need to put the name of the gene on the label. The second thing we might think interesting to do is to actually order the genes, so they are sorted by level of expression. So that's what I was doing here, but the challenging thing in our situation is that we have one vector with the genes, their names, and one vector with a level of expression. So we need to sort the level of expression. That's the thing we want to have that nice stair looking plot. But we also want the gene names to be sorted to match that new order we have. So if you remember, I think it was on the first session, we saw the function sort to sort a vector. So that's the one we're using here. But instead of just creating a new vector that is sorted the order we want, we are actually gonna record 2 elements. The first thing is the results now sorted, and the second thing is the order in which they were. So for instance, if the 10th gene in our data set was actually the one with the lowest level of expression, then we're going to create a new vector where on the position 1 we have the value 10, which is saying in our new vector, the gene we have on position 1 is the gene that used to be on position 10. So the way to do it is actually super convenient with MATLAB. As you sort your level of expression, so the expression result, you can directly store those 2 information, so the new order and the old positions, by using this syntax, where instead of just giving one name to store one vector, you give 2 names. So here, yeah, those 2 elements, the x1 result sorted and the kk vector together. So if I write that, I'll show you what it looks like. So if I execute this, Now you can see we have generated 2 elements here. We have that one. I can click on it. You see that's the level of expression we have in the order. And we have KK, which is telling you that the gene that is now on the first position used to be on the 18th position. Okay, so I have questions. The first one is, can we have subgroups in bar plots, such as time points? So I'm not completely sure what you mean, but I assume maybe you mean something like if you have a big data set where several genes were measured at different time points, you having them plotted on different bar plots. So if you do something like that, it depends on your, I mean, you can do it. I think more or less anything you want to do, you'll be able to do it at some point, just more or less straightforward. But either you have them in 2 different columns, in which case, you know how before we were using this. And so instead of having, plot X and yeah, I mean, that would be the same thing. That would be like column for time point 1 and column for time point 2. And you would have two things like that. If there are the more on the row, like the tidy data format, if you're using more the tidy data format, for which we have each row is 1 different observation. So you have gene 1 time point 1 and gene 1 time point 2, gene 2 time point 1, and so on. You might, if you want to have subplots that way, you might have to separate first in 2 data sets. So for instance, we've seen how you can do it with, for loops. You store all of them in one data set, or the first time point in one data set and the second time point in a second data set. And then you can plot them in subplots like that. And the other question was, how about error bar? So I have not used error bar recently, so I would just Google how to put error bars on MATLAB plot, and that should address your question. We can try doing it. Well, I'm gonna take that. So for instance, that one. So yeah, that's another good thing. Actually, the MATLAB, MathWorks, the MATLAB developers, they have some active, like they have a pretty well filled documentation and also active forums where people ask questions and they get answered. So yeah, you can see here the command is the error bar. So you can, so it's the same as before. You put your bar first, you hold on, or you can open the hold on before, put the bar, and then add the error bars. And so here they do all the customization in the command line, and that's what we've done so far. But I just show you a little bit later. You can directly edit the aesthetics of your plot within that window. I'll show you a little bit later. And so going back to our sorting question, we had someone asking what exactly KK is. So KK is a new it's a new vector. It's the one that I have here. So yeah, it's a new variable. So when I executed that command line, I created 2 vectors. The first one is the X1 result sorted that had all the level of expression sorted from the smallest one to the largest one. And then I had KK, which is, it's a vector that is as long as the original vector we were working with. So here 59 genes. And for each gene, it's storing at the new position what its former position was. So for instance, the gene that has a level of expression of 0.49. Now it's the first one in our sorted vector, but it used to be at the 18th position. And yeah, so Ricardo, you're asking why calling it KK. You can call it whatever you want. So it also works if we use the name you suggested. So the reason why I messed up. The reason why I used KK is just because we're gonna use it later, and so sometimes it's annoying when you have two type things that are too long, like variable names that are too long, but it's the same. You can give the name what you want. So for instance, here you can see the same thing. Okay. So moving on from there. So once we have those two information, we can now sort the names. So if you remember what I told you before, so when you work with, for instance, if I have a matrix or a vector, that will be 1, 2, 3, 4. And I want to create a new one from this one, but change the position. So for instance, I want maybe using, okay, I'm gonna change that. I'm gonna call them 10, 20, so it's less confusing. Yeah, you can, you can call, for instance, if I call the alpha 2, that's gonna return 20. And then if I call alpha 1, 10, and alpha 4, that's gonna be 40. So if I say to MATLAB, call the X1 gene, so that the vector with the name of the genes, but instead of ordering from 1 to 59, you order it following the new order. So the order that I stored in KK. So for instance, if I do it here, let me just check that I don't do, okay, so that's. So if I do that, I'm gonna have the same thing coming back to me. So reverse, no, wait, I forgot the alpha. So here reverse is looking exactly like alpha. But if I do, for instance, I inverse the 4 and the 1. Now I look what it looks like. Then you see that it inverse the 4 and the 1. So when I do that, but on the X1 genes, and I say, instead of using that vector I created here, you use the vector KK I created before. And with that, you create a new vector that is just the same value as X1 genes, but ordered following the order given by KK. And if I run that, so let's compare the two here. So you can see here that was the original order we had, which was actually alphabetic order. And now we have the new order that is matching the order that we have here. So now that we have this information, we can now plot our gene expression levels, but sorted. So here it is, it's sorted, and we can add the the names here. So the line looks a little bit complicated because if you try to put all the names, you know, they overlap together. So I'm saying you add the ticks, so the tiny bar here, only once every 7 gene, so it's easy to read. And for the label, you took the corresponding one in name sorted. So yeah, I'll give it a different name here. But yeah, so that's the kind of line you use for that. And so you can get something like that. And then another kind of plot you can do is a histogram. So for histogram, that's simply the function histogram. So yeah, I assume you're familiar with the difference between a bar plot and an histogram. But so here we don't care whether it's sorted or not anyway, because it's gonna be sorted by level of expression anyway. So now I have it here, and so yeah, that would be worth adding legends. On the X we have the level of expression, and on the Y we have the number of genes that are that fits into that express that corresponds to that level of expression. So for instance, if I go back here, so what I did here, I won't type it all, that's going to be boring for you to watch. Okay, so we did that. I'm just going to do it again. Oh. We put the two together. So here we have the genes ordered by level of expression. And here we can see how many genes we have fitting in different categories of level of expression. Count of genes, so that we have, I don't know, 18 genes expressed between 0 and 10 units. So you can see here, I did 2 subplots. Subplot 1 with the bar, I put all my information that I wanted to put. So that's what's happening here. And then subplot 2 with the histogram, and same, all the information I wanted to put. So again, like the command to generate histograms or bar plot or whatever is always different from an environment to another. So for instance, histogram, sometimes it's hist, sometimes it's histogram. So if you don't remember, you can try a bunch and you get error message for the one that are not working, or you can just Google histogram MATLAB and you will have that answer. One thing MATLAB is very famous for is 3D plots. So that's yeah, one of those environments where it's just, I don't know, it's doing nice 3D plots and they're quite easy to handle. So here I did the same as I did before. So I'm gonna again clear all that. So I generated data. So you can actually also use, if you want to generate grids, so yeah, you can use that function. So I'm showing you what it looks like. So it generated some X and some Y that takes those values. So for instance, if I, okay, there are lots of values, so it was not a good idea to just print it, but you can see you have, yeah, a grid of X and Y value that goes from point 2 to point 2. And then, so that's our 2D plan. So that's, if I wanted to plot, actually I can. So I have something like that. So that's just the empty grid. So you see, I'm still stuck in the subplot I started before. So that's why it's useful to, maybe I'm gonna do close all. Oops, I run the scripts. You've been spoiled. Okay, so I closed everything. Now I do that. So I have my grid to start with. And then I run this to define the third dimension. So that's not really important. I mean, that can be whatever. It's just for the example. And then when you want to plot here, you're gonna use surf for surface, and you put the X, Y, and Z together. And here you go. So one of the reasons why it's quite practical with MATLAB to render 3D plots is notably that you can rotate them. So when I put my mouse on the plot, I have this menu appearing here. I can click on that and I can rotate, so I can see, you know, if you want, for instance, if you want a heat map instead of a 3D plot, you can get that, and or you can go back to 3D plot and explore whatever side of the plot you want. And we're gonna see right now what I was telling you about regarding how practical MATLAB is for plots. You can actually change lots of things straight from that window. So here I showed you, you can change the, I don't know, the direction, but you can actually change all the elements of the plot. So you go in edit and you can go in figure properties or arcs properties and change whatever you want to change on the color map. Sometimes it's, if you don't have a very, I don't know, powerful laptop, like it's my case, it can take sometimes a few seconds, especially when you're running 3D plots. It's quite slow. So anyway, you can change whatever you want. I'm not gonna show too much because it might take 5 seconds for anything I want to do. I'm gonna do something a bit more straightforward. So maybe like the figure property might be running a bit faster. But yeah, so anyway, you can change. Okay, it's very slow. Sorry, I apologize for that. I'm at home, so I have only my personal laptop, and it's it is not a huge machine. So yeah, here I showed you example. You can change the position on which you want the plot to be, or I don't know, you can print and export too. And what is great is that when you change something, so for instance, I think it's here now. Okay. I don't know, you can change the font and whatever. If you change anything, so okay, let's try something. We're gonna put whatever font. So you see the font changes a little bit. I'm gonna rotate it a little bit too. Okay, no, it's too slow, sorry. Then you can go on file and you can generate code. So it's gonna take a few seconds to run too. But it's gonna generate a code that appears here. And you see it's, for instance, saving like the position of the axis, and that will also save the angle of your 3D plots. That can change, for instance, here I changed the font, and so that's here. And so you can edit as much as you want in your in the editor, in the figure editor. And then export the plot. And so it means that every time you will generate, for instance, update the data and generate that plot again, you won't have to, try to play again with finding the ideal position, or like if you want to generate three times the same plot, but you want to make sure that the angle you look at is the same, so you can compare the plots, like 3 times the same plot with different data, for instance. Then you can use that code that you generated to create those plots. So you see it's a function, so you can save it as a function, and then you just have to change the data you put as input in there. So that's a very powerful tool. I don't know any other programming environment that has that kind of stuff. So if you have a very figure intensive project, that's definitely worth working with that. Okay, that's not what I wanted. Okay, do you have questions about plotting? Are you happy? Okay, so I'm gonna move on to the next thing. So again, like, so yeah, figures is really about trial and error. So, you know, any figure you wanna do, just play with it. And because of that graphic editor, the figure editor, whatever you wanna call that, you can, it's easier than, you know, for instance, I mostly code in R, and so every time I want to change something on my figure, I have to change it in the code, and it comes with bugs and stuff. While here you can just play straight from the thing you're visualizing, so it's very useful. Again, so now I'm gonna use the 20 minutes we have left to give you a very brief introduction to dynamical system modeling with ordinary differential equations. So yeah, here the idea is to model a biological process with equation, and that's something that is pretty common in MATLAB. Lots of people doing modeling use MATLAB, and I showed you actually on the first day some examples of epidemiological models that were run with MATLAB. And notably, one of the tools people use a lot are ordinary differential equations. So they're very good for temporal dynamics. So differential equation is because you can, you know, you're looking for the derivative of something across a variable. And so in most of the case for those kind of questions, you're looking at changes in time, changing through time of a variable. So for instance, the concentration of a substrate, the number of infected individuals in the population, and so on. So maybe during the COVID-19 pandemic, for instance, you've heard about SIR models. And so SIR models are ODEs with where the variables you track through time are the number of susceptible, infected, and recovered individuals. That's what the SIR stands for. So you can use this kind of models to test or generate hypotheses, or to see if you can find a mechanistic explanation to some results you've observed. So for instance, you've observed variations of whatever substrates, and you wonder if it's because it's due to the variation of another substrates, and you can see if mathematically it fits with those kind of models. Also sometimes just to visualize like more clearly results. So we start with a pretty simple example with two metabolites A and B forming a polymer AB. So we have A and B, and they bind together, and they form our new metabolite AB. So the questions we can address with ODEs, so for ordinary differential equations, how do the concentration of A, B, and AB vary over time? And so you can actually write that in math form. So the concentration of AB over time, the variation of concentration of AB over time will be proportional to A and B. That's, I think, pretty intuitive. And if you had some chemistry classes before, I'm sure you've seen that 1,000 times. But yeah, if you don't have A anymore, you won't be able to form AB, and the more A and B you have, and the more AB you'll be able to form, and so on. And so the way to write this is that the concentration of AB over time, so the variation of concentration of AB over time is a linear function with just a proportionality factor K, AB. So that's the reaction rate K times the concentration of A and the concentration of B. The concentration of A is also dependent on AB, but this time it will be consumed as AB is formed, and same for B. So we have those three relatively simple equations, and yeah, all you have to understand is that the AB, the polymer AB is formed as a rate, the concentration of polymer AB over time will depend on the concentration of A and B you have to form it. And the concentration of A and B over time will depend on the rate at which they are consumed to form AB. So those three equations are related together. So that's what we call a system of differential equations, because we have three differential equations that rely on the same parameters, and notably here A and B, or here A and B, you know their value over time because you know how they vary in the previous differential equation here above. And so the way we can do it in MATLAB, and so the why people do it with MATLAB often is because MATLAB has a quite efficient way to write those kind of models and to solve the equations, so notably to find the actual variation over time based on those differential equations. So the way it works is that you have to write first an ODE function. So that's a function that you write that contains all the information regarding the ODEs. So here are the, okay, what information do we have? So you see we had one parameter in our model that was K. That's the rate at which the reactions occur. So we'd have to define that parameter. You can put whatever value for that example, it doesn't matter. Then we have a binding rate, KAB, that appears several times. So here, sorry, here, yeah, it appears here, and its negative value appears here. So we can define that binding rate, so we don't have to write it again every time. And so here A and B are going to be x1 and x2. So we define our binding rate. We have to define a matrix that's going to store the values that are generated each time at each time point. So you remember zeros, that's a function we saw yesterday that allows us to create like a matrix of zeros. So we start with a matrix with, so you see X is something we're gonna put that's actually gonna be the vector of metabolite. So that's gonna be 3, the length of X. So because the length is the largest dimension, so it's gonna be 3, and 1 because we start just with 1 at the beginning. So we have 3 rows and 1 column. So for 3 metabolites and just 1 time point to start with. And then we write our differential equations, and we can just reuse that binding rate we defined before. So the key elements here are, you define the parameters, then you define the key rates that are important in your system. So here we can see the only one that is really important is K times concentration of A times the concentration of B. And that's what we call the binding rate, because that's the one we're going to be reusing every time. And then we have we have to create a matrix to store the value we're going to obtain at each time point. We start just with 1, and then we write our differential equations. So that's our function, and that's the way it's written. So yeah, there it is. So you can see here, for instance, I put, that's the information that will appear if you type help in MATLAB. And then once you have written that function, so you can see I named it FODE file. You have 2 arguments. You have to put the time points and the metabolites, but actually the way you're going to use that function is to put it straight in the ODE solver. So here I'm going to have T and Y. So T is for the time and Y is for the concentration that I observed. And that's going to be our output. And I'm using the ODE solver that is already predefined in MATLAB. That's the function ODE 15S. Then I have to inform which function you have to use. And if you remember before, I need 2 arguments for my function, the time and the metabolites. And so what I put, the I put them here. So I don't put them as in between parentheses in here, because think about this as another function. And so I'm saying the argument of that function are one, the function, the OG function I want to use, two, the time span, or yeah, the t and x I'm gonna put in the ODE file function, if that makes sense. So here is a time span. So I've decided to go from 0 to let's say that's 2 seconds, and with a time step of 0.1 second. And then the initial conditions, I had 3 metabolites, so I have to put a vector of 3 values. That would be the concentration of A, concentration of B, and concentration of AB. And that has to match the order you add your stuff here, your equations here. And so you can see here it's going to use X1 and X2 to start with, and then it's going to follow whatever change are driven by your differential equation, your system of differential equation. So when you execute this function, it's going to generate those 2 outputs. Like when you remember when we use the sort function with 2 expected outputs, we had 2 different vectors that were generated. That was the vector value sorted, and the KK, or like position, original position, or whatever. So here it's gonna create a vector with the time points and a matrix with the concentration for the 3 metabolites. So I'm gonna again spare you watching me type that. So I've explained to you what it was. So here is our function, and then again I'm gonna do my usual maintenance work. And I have everything written here. Okay. So I have my function here. That's the one I just explained. And here is how I'm gonna execute it. So I execute this. It's pretty fast to run because it's a quite simple system, and I didn't put that many values, but if you have bigger models, that can take some time to run. And then I plot, and it's in the back, and you can see here the concentration of my metabolite. So I didn't put any legend, but we can guess. The one that was starting at 0 was the AB. So it started at 0 and it increased. It increased as A and B are going down. So A was the one that was starting at 1, and B is the one starting at 0.5. So when you have a system like that, it's, and you could have guessed, and I would have followed that kind of dynamic. So I'm not sure you needed a model for that. But if you have more complex systems, then it becomes useful to find out what is the limiting reactance, or find out, what is the effect of different like how your system will change if some specific parameters change. And so, for instance, if we move on, so here that's the plot we just got. If we decide to have a little bit like a model that is tiny bit more complicated, for instance, we can add a new metabolite C that will appear from the polymer AB. So I added it here. I added it here too. So here we have a new rate, reaction rate K2, and that's gonna depend on the concentration of AB. And so what I did here is adding my new parameter here, adding my new rate here. I mean the new reaction, equation here, and then I use it here. You also have, in that case, to account for the fact that AB is consumed when it turns into C. So we also added that here in the equation here and in the model here. So that's our new system. We run it the exact same way, and except that we have to add an initial value for C2. And we have something like that. So you can see, for instance, how adding a new biological process in your system impacts the concentration. And so, for instance, here we're thinking conversion rate that can be, like if there is some kind of medication you can take that can prevent the accumulation of dangerous metabolite, for instance, how you can explore which conversion rate you need to have an efficient limitation of the accumulation or something like that. And then to move to this kind of actual, like more interesting question, one thing we often do is sensitivity analysis or exploring the parameter space. So here what we did is we have that system that was just defined with our three or four metabolites, so A, B, and C. And we wonder how the behavior of the system, so the concentration of our metabolites, change over time depending on the value of B you start with. And so you can see the way I did that is I generated a matrix to store the results, so that's that becomes important later. I created a for loops. I wrote a for loops in which I'm gonna execute that solver at every iteration. But at every iteration, I'm gonna start with a different value of B. And that value will go from 0 to 1 and with a step of 0.05. Within my loop, I execute the ODE solver. So every time I get a new T vector and a new Y matrix with the concentration of all metabolites at each time point. And I want to store that in my matrix of time course. So you can, yeah, actually it's not visible here, but yeah, I every iteration of the loop, I add a new element in my matrix that will store the results I got from there. And here you can see I use I use this notation because to save some memory, I'm gonna only save the concentration of AB instead of saving the concentration of all the metabolites. I'm only saving the concentration of AB, which is the third column in my Y matrix. And then I increment my index. So here I have two indexes that are together, increasing together. The first one is II, which is a concentration of B, and the second one is what I call the current index. And it cannot track the concentration of B because for each new concentration of B, I will have a new index. But this one needs to go needs to increase with steps of 1, not steps of 0.05, because this is the index in the matrix. So in the matrix, a position can only be an integer. It cannot be a decimal. So I have to have that additional index that corresponds to the position in the matrix in which I will store the results. So it could be, I could have done it the other way around. I could have I going from 1 to, I don't know, 1000 and increase my concentration or increment my concentration of B here. Both will be equivalent. You can plot at each iteration. I commented those lines because when I run that code, it takes lots of time to generate the plot each time. And yeah, so if you don't want to spend like 5 minutes waiting for your computer to be ready, you can remove that. Those plots were generating that kind of thing. So it can be interesting to see each iteration, but that's not necessarily the final result we're interested in. The final result we are interested in that case is the concentration of AB as a function of time and as a concentration of as a function of the initial concentration of B. And so, yeah, you can see, for instance, considering that B is a limiting factor, how much the system will be impacted by the concentration of B. So that's, yeah, the kind of questions you can explore. So all the codes are in the drive if you want to try to run those similar kind of stuff. And yeah, any questions? That's the end of the workshop. Any question on that part or on something we've seen earlier? So again, like this part, that's not necessarily something like all of you who are doing genomics or image processing, you might not need that. It's really for people who are doing modeling, yeah, like biological modeling. That's one thing MATLAB is very powerful for. So that's a good example of MATLAB strengths. Okay, I'm gonna stop recording and then I'm gonna ask again if you have any questions.